You walk into a doctor's office, hand over your medical file, and watch them feed your entire life history through a modified language. AI, just so the screen can tell you your pancreatic cancer will arrive in precisely 19 years. We are forcing AI to predict our individual medical futures and tearing apart its underlying architecture to make it run faster. We are also hand-feeding it forgotten languages to keep it from failing.
Generative transformers are literally moving beyond text to map human disease trajectories. The Delphi 2M model basically modifies the standard GPT-2 architecture to create those predictions. Standard language models track the fixed position of words in a sentence. Delphi discards positional encoding entirely.
Discovering your septicemia risk drops off a cliff after 5 years feels like checking your credit score the day a bankruptcy finally falls off your record. It sort of provides this sudden release from a massive mathematical penalty. I get stuck on how the math actually maps a human life like that.
They encode your continuous age using mathematical sine and cosine functions. The system tracks 1,258 distinct states. It covers over 1,000 top-level ICD-10 disease codes. The system also captures lifestyle factors like body mass index and smoking habits.
It tracks alcohol consumption and your eventual death, too. Training a model of this scale required massive data volumes from highly structured environments. The researchers fed the model the medical histories of 402,799 UK biobank participants.
They validated the results against almost 2 million Danish citizens using their national health registries. Generating predictions across those overlapping variables requires an exponential waiting time mathematical approach. The algorithm samples future health trajectories up to 20 years out.
Human biology does not happen in neat, evenly spaced sequences. You might get a flu diagnosis in January, break your arm in February, and then not see a doctor for 7 years.
Every single disease code acts as an independent ticking clock inside the algorithm. The model calculates the speed of each individual clock based on your past medical data. The exponential waiting time approach ensures the math holds up when events overlap.
The model accurately tracks temporal effects. A cancer diagnosis elevates mortality risk for years. The AI pays attention to that cancer token long after the doctor first recorded it.
The mortality impact of a heart attack or septicemia drops off sharply. The AI learns to stop penalizing your biological profile once you survive the initial acute phase. The algorithms cannot distinguish between a person who is genuinely biologically failing and a person who just interacts with the medical system more frequently.
The AI blindly learns the biases of the human healthcare system it digests. Getting a hospital record makes the AI predict you will get vastly more diseases simply because hospital records capture sicker people. The developers built an internal map to show exactly how the AI arrives at these predictions using Shapley additive explanations.
They call them SHAP values. This concept originates in game theory. It calculates how much each individual player contributed to a final score. Every past diagnosis acts as a player contributing to your future disease risk in this medical AI.
The researchers examined a trajectory where a patient developed pancreatic cancer at age 68. The internal map showed that a series of minor digestive tract diagnoses recorded years earlier combined to elevate the patient's pancreatic cancer risk 19-fold.
The moment the pancreatic cancer diagnosis appeared on the record, the AI showed the patient's mortality rate jump 10,000-fold.
Teaching the AI about disease involves tracking those precise data points. Teaching the AI about health requires structural manipulation of the timeline.
The developers randomly inserted blank padding tokens into the medical histories at an average rate of 1 per 5 years.
Without these synthetic padding tokens, the AI only sees dense, chaotic clusters of illness. A patient goes to the hospital, gets 4 diagnoses in a week, and goes home for a decade.
The AI processes that data and assumes the intervening decade of health did not exist. The padding tokens force the AI to recognize long stretches of healthy time.
Modeling younger patients who rarely visit hospitals becomes impossible without forcing the machine to acknowledge the absence of disease. The engineers found a massive flaw in the data collection process because the foundational UK Biobank dataset contains a severe immortality bias.
Because the UK Biobank only recruited living people aged 40 to 70, the AI falsely thinks mortality is 0 before age 40. The data contains 0 deaths for anyone in their 20s or 30s.
Dead people cannot enroll in a medical study.
The model processes that data and concludes that human mortality is mathematically impossible before the 4th decade of life. The risk suddenly jumps at recruitment. The model internalizes the artifact of the study design as a biological law.
Predicting a 20-year medical history requires an AI to hold massive amounts of past data in its active memory. Standard transformers crash under this weight. They hit the quadratic bottleneck of the key value cache.
As context doubles, computing cost quadruples. Processing a lifelong medical record maxes out the memory hardware almost instantly. IBM Research collaborated with Carnegie Mellon University, Princeton, and the University of Illinois to build Bamba 9B.
They designed a hybrid model. Bamba mixes the attention mechanism of a traditional transformer with state space models.
Engineers traditionally use state-space models in electrical engineering and control theory. They maintain a fixed-size hidden state that summarizes past information rather than recalculating everything. The model selectively forgets unimportant details to save memory.
Carrying the key value cache is like dragging every single grocery bag you have ever purchased back into the store just to buy milk. State space models just bring a summary receipt.
The S4 model and Mamba 2 architecture introduced a gating mechanism to filter out irrelevant information. That hardware upgrade allowed state-space models to match standard transformer capabilities.
Silicon Valley is basically digging up control theory math from the 1960s to fix the embarrassing fact that their multi-billion-dollar chatbots have the short-term memory of a goldfish. Bamba processed 3 trillion tokens during its training phase.
The model natively handles 32,000 token conversations. The developers expect it to scale to handle 1 million tokens. Researchers use quantization to shrink Bamba from 16-bit floating point precision down to 8-bit.
Stripping away unnecessary precision cut the model size from 18 gigabytes to 9 gigabytes. The AI sort of rounds off the long decimals in its internal calculations. Bamba runs twice as fast as similar transformers.
Bamba also matches the accuracy of Meta's Llama 3.18b model. Lowering the bit width removes the excess computational baggage.
The engineering team actually integrated Bamba directly into VLLM. That serves as the standard open-source inference server.
Supporting state-space models requires bespoke state management. It forces the developers to rewrite how the server handles memory allocation.
We jump from the massive scale of IBM's 3 trillion token English models to the agonizing human labor required to make AI work for a language with zero digital footprint. Kashmiri is spoken by nearly 7 million people but lacks natural language processing resources.
Researchers manually created a dataset of 15,036 news snippets. They categorized the snippets into 10 domains. They covered medical, politics, sports, tourism, and education.
The snippets also included art and craft, environment, entertainment, technology, and culture. The researchers translated them using Microsoft Bing. Native speakers then executed a rigorous 2-step manual refinement to fix lexical issues.
They needed to ensure cultural authenticity. The manual refinement achieved a Sacred Bill use score of 44.85. A fine-tuned parsed uncased model hit a 9.8 F1 score.
They measured the semantic similarity between these domains using mathematical similarity metrics to prove the dataset had strong vocabulary diversity. The similarity score between the medical and entertainment domains was incredibly low.
The manual curation successfully isolated distinct linguistic patterns. They measured the translation quality using a back translation method.
Measuring translation quality computationally requires comparing the AI's output against a human reference translation. They achieved this using a metric that counts overlapping sequences of words.
They used a rigorous mathematical scoring system to prove the machine's translation was culturally accurate. They hit numbers that rival commercial translation engines.
We have AI that can hallucinate a Shakespearean sonnet in seconds. We are still forcing humans to manually hand-correct 15,000 translated news snippets just so a machine knows what a Kashmiri sports article looks like.
The Bloom 560 MAM model failed completely in a zero-shot setting with an F1 score of 0.04. After the researchers fine-tuned Bloom, it rocketed up to 0.97.
I question why researchers forced massive large language models into this tiny dataset in the first place.
Traditional machine learning actually crushed the deep learning models here. A stacking classifier using IndicBERT v2 embeddings achieved 95.6% accuracy because IndicBERT was specifically pre-trained on Indian languages.
The stacking classifier merges logistic regression and support vector classifiers with an AdaBoost framework. The FLAN T5 base model failed entirely. Its tokenizer did not understand the Perso-Arabic script.
The tokenizer spit out unknown tokens. It triggered a default fallback mechanism instead of processing the shapes of the alphabet. The entire neural network sits idle behind a digital wall, simply because the initial text processor fails at the very first point of contact.
Failing to classify language because the tokenizer spits out unknown characters feels like getting locked out of your own house because the voice-activated smart lock refuses to recognize your morning voice. We are watching an architectural mutation. Models are getting highly specific.
They are predicting our individual biological decay down to the day. They are rewiring their memory banks to run cheaper. They also rely heavily on human manual labor to understand the rest of the world.
Delphi 2M can generate fully synthetic humans from birth that perfectly match population health statistics. Bamba is expanding the context window to near infinity. You have to wonder how long it will take before an AI runs a completely synthetic version of your life, gets synthetic fatal diagnosis, and processes the grief all before you even finish your morning coffee. Goodbye.